All right, so lesson 2-3 polynomial functions and the graphs. So last time was just quadratics. Now we're building into just any type of polynomial function. So it could be bigger than a quad, and what's all going to happen. So you have 100 yards of fencing to enclose a region. Find the dimensions that will maximize the enclosed area. What's the maximum area? So this was building off of last time. We were using the quadratic functions, and we were finding the what's the max or the min of them. So 100 yards of fencing. So we're enclosing a region. We're going to do a rectangular region. So perimeter would equal twice x plus twice y. X being the width, y being the length. So we know we have 100 yards to go with that. So we can sub that in for the 2x. Or for the b, sorry. Now, what we're trying to find is the maximum area. So area is going to be then x times y. So I'm going to solve this one for y. So I'm going to subtract the 2x over. So 100 minus 2x equals 2y, divided by 2. So 50 minus x equals y. So what I'm doing here is I'm solving for the one equation, or this one variable, so that I can put it into the other equation for that variable and have just one variable. So my new area equation now is going to be x times our y, which is 50 minus x. And then we're going to distribute that x in and have an area equation of 50x minus x squared. So over here we're going to do the b, negative b over 2a. So negative b, which is going to be 50, because remember the b always is with the x, over 2 times a, which is going to be negative 1, because that's what's in front of x squared. So the negatives will cancel, and 50 over 2 equals 25, which is what x is. So if x is 25, 50 minus 25 would give us y, so in other words 25 is y. So to get the max area, because we always have to check how we answered the question. Well, the maximum area is x times y, so 25 times 25, a of x would equal 625 yards squared. So, official definition of a polynomial function. Really what it's saying here is this. The degree is going to be the biggest exponent of our numbers. So a polynomial could have just a constant there. It could have an x plus a constant, an x squared plus x plus a constant, on up. So as long as we have all positive whole number exponents, we can really have about anything for an exponent there. Now, like I said, degree is always the biggest exponent. And we're always dealing with one variable here, and the one that has the highest power is also called the leading coefficient. And we're going to use that here in a little bit. So right now, I know it's a lot of talk. Once we get to an example, it'll make more sense. But graphs with a degree 2 or higher will still have smooth curves. Typically, if it's degree 2, that would be like a quadratic and x squared. We have a parabola. Well, as we get into higher degrees, it's going to affect the shape of the graph a little bit, but we're still going to have smooth curves, and we're going to be continuous. We're not going to have any breaks, no jumps, nothing like that. So where that leading coefficient comes into play is that end behavior. So the ends of our graph, what they're going to do, whether they're going up to infinity, down to infinity, or if they're going to go towards a number, is all going to be determined with the leading coefficient here, the leading coefficient test. So when it's positive, we're going to have 4 things going on here. So if we're looking for the leading coefficient, so the number in front, and the biggest exponent. So the biggest exponent, if it's an odd degree, when the leading coefficient is positive, it's going to fall to the left, rise to the right. So think odd, positive, ends are going to do something like this. If it's odd and negative, then it's going to go the other way. The left will go up, the right will go down. If it's even, So as you see, odd, they're going opposite directions. So positive, left is down, right is up. Negative, the right is down, the left is up. Even, positive, they're both up. So they're both going to go the same way. Whereas if it's even, negative, they're both going to go down. So that's what the ends are going to do. So it's not describing what's going on in the middle, but it's just if we know that it's an odd exponent with a positive number in front of it, then we're going up and going down. Down on the left, up on the right. If it's odd exponent, negative number in the front, then the left is up, the right is down. If it's even exponent, they're both going to go the same way. So if it's positive, they're both up. If they're negative, they're both down. And that's really what's being described here. So use the leading coefficient test to determine the end behavior of the graph. So this is where we're looking. So first off, the exponent were odd. Then the number in front. If there is no number in front, it's 1. We don't have a negative, so it's going to be positive. So positive and odd, the left is going down, the right is going up. So left, down, right up is what's going on there. Now in this next one, again, we're looking here. So the exponent again is odd, but then our number in front is a negative. So negative and odd, now it's going the other way. So left is up, the right is down. So what's going to happen is our graph is going to be something where maybe it's doing like one of these or whatever. But the ends of the graph in here doesn't matter so much. It's the ends are going to be doing that stuff. That's what that leading coefficient test will do for you. It'll tell you which way the ends of the graph are going to do. So which graph, one that either falls to the left and rises to the right, or one that both fall to the left and right, would be this graph. So again, if we look here, our number in front is going to be negative. Our exponent is even. So if it's even, they're both going the same way. So in this case, it's going to be fall, left, and right. So both sides of our graph are going to be doing that. Now, we've talked about this a little bit before, but zeros are those values of x in which f of x is going to equal 0. We also call them roots, we call them solutions, we call them our x-intercepts. So to find the zeros of our function, here we have 4 terms. So what we always want to check when we have more than 3 terms is, can we do this by grouping? So if I group the first 2 together, I could pull an x squared out. What would be left would be x plus 3. This back one, I'm going to pull a negative 1 out and have x plus 3 left. So what this goes to then is x squared minus 1. Because remember, the numbers in front go into one parenthesis. The ones that are the same are the second parenthesis, x plus 3. So x squared plus 1 will break down to x plus 1, x minus 1, as it is a difference of squares. So in this case, our zeros are going to be x equals negative 3, negative 1, and 1. Because we would set each of these equal to 0, we'd subtract the 1 over to get our negative 1, we'd add 1 over to get our positive 1, we'd subtract 3 over to get our negative 3. So in this case, we have 3. But the first thing you should always check is, can I pull a common factor out? So I'm going to pull out a negative x squared. So what would be left would be is x squared minus 4x, because it'll be the opposite sign, and then plus 4. So negative x squared would factor out this here to be x minus 2, x minus 2. because negative 2 and negative 2 make 4, but yet negative 2 and negative 2 added together make you negative 4 from the middle. So if we solve this one out, we're going to get x equals 0 from the x squared, because if you square root 0, you're still 0, and the negative won't matter. Here you'd add 2 over, same thing here, add 2 over, and so we're going to get 0 and 2. Now, one thing you should notice here, so up here, none of these repeated. There was only one of them that was this, one of them that was that, one of them that was that. Here, technically, there'd be 2 of them with the x squared, that's going to give you 0. Here, there's going to be 2 of them that can then give you 2. That there is your multiplicity of your x-intercepts. So it's how many times that 0 occurs. If it's an odd multiplicity, so if it's an odd amount of times, so if it happens once, if it happens 3 times, happens 5 times, then it's going to be a cross at that point. If it's even, then it's going to touch at that point. So touch and turns around when it's an even multiplicity. So if I look back at this last one here, so these were all happening one time. That's an odd amount of time, so these would all touch. No, don't touch, they would cross, sorry. X-axis at those points. Here, these are both evens, so they would touch and go back. So what we're talking about is, so down here we would come down, we'd touch it and go back up. Where up here, we're going to cross the x-axis 3 times. Okay. So here it's already factored out. So multiplicity is determined by the squared. We know there's 2 of those, which means it's even, so whatever we solve for there, it's going to touch. So 2x minus 3, if we set that equal to 0, we'd add the 3 over, so 2x would equal 3, divided by 2, x would equal 3 halves, and it's going to touch the x-axis at that point. This other one, there's only a single, so x plus 1 equals 0, so you'd subtract 1 over, so x equal negative 1. Here it's going to cross, because there it's happening only one time. So odd it crosses, even it touches. So again, if we had our graph, so it doesn't matter what's going on behind it, but at negative 1 here, we'd be crossing, and at 3 halves, we're going to be a touch and back. Or maybe it's the other way where we're crossing, touch and back. You know, that'll depend, but this is the idea of what's going on. So at negative 1, at 3 halves. So we're going to cross here, only touch here. Now, we have an intermediate value theorem for polynomials, which pretty much says we're going to check the endpoints. And so if they're opposite signs, then we know somewhere in our graph there's a point exists where our y is 0. Which would make sense, because if we're going from negative to positive and we're continuous, we don't have any gaps or jumps, somewhere we have to cross over the x-axis to get to the other side. So if we're negative and positive, we'd have to go from negative to positive, we'd have to cross, or if it's the other way around, from positive to negative, we'd have to cross. So here's what you do. So it says show that there is a real 0 between 2 and 3. So all you have to do is this: f of 2, f of 3. So if we put 2 in here, 2 to the third is 8, minus 2 times 2, which would be 4, minus 5. 8 minus 4 minus 5 is going to get us to be negative 1. We're going to put 3 in there. 3 to the third is 27. Minus 2 times 3, which would be 6, minus 5. Throw minus 11 from that, and we get 16. So, negative to positive. So there has to be a switch. So this is how we'll write this. We'll go 3 little dots, which means therefore. So therefore, by IVT, which is the intermediate value theorem, there exists a 0 between 2 and 3. So first step, put the one endpoint, show it's positive or negative. Put the other endpoint in, show that it's the opposite sign. So therefore, by IVT, there exists a zero between those two endpoints, in this case 2 and 3. So turning points is another thing you have to look for. Turning points are going to be points in the graph in which the direction changes from either decreasing to increasing or increasing to decreasing. How we find that is we're going to take whatever the degree is, subtract 1, and that's the max amount of turning points that can happen. So when you graph these, you want to follow this. First off, find that leading coefficient test, determine what the end behavior is going to do. Then find your x-intercepts, set your function equals 0, solve that out. And then keep in mind what the multiplicity is. Remember, if it happens an even amount of time, it's going to touch and turn around. If it's an odd amount of times, then it's going to cross over at that point. So if x is greater than 1, the graph is going to flatten out at r, comma 0. So hold that thought. Don't worry so much about this one for right now. Because right now I'm drawing a complete blank at what I'm trying to say there. Anyways, then you're going to find the x-intercept by computing f of 0. So put 0 in for x, and you'll solve that out. One thing we got to keep in mind is we want to look for symmetry, because that'll help us draw the graph. So back when we talked about symmetry, if we put a negative x in and we get the exact original equation out, then we're going to have y-axis symmetry. And it's origin symmetry if we put a negative in and we get the complete opposite out. If some changes, some doesn't, then there's no symmetry. Then lastly, check for the n-1 turning points. So we're going to put that all together and graph this one here out. So we're dealing with x to the 4th. So this is a bigger one than what we're used to, but we can still find the generic graph for it. So number one, we're doing the leading coefficient test. So we're looking right here. We are even and we are positive, which means both up. Both endpoints are going to go up. All right. Step 2. Looking for x-intercepts. So I'm going to do it over here. So we have x squared minus 2x squared plus 1. So this should be x to the 4, sorry. So we're going to factor this. So we're going to go x squared and x squared. To get a minus 2, they both have to be minus 1s. Because negative 1 times negative 1 is a positive 1, but negative 1x squared and negative 1x squared make 2x squareds. Now, both of these are difference of squares, which would mean they break down to x plus 1, x minus 1, x plus 1, x minus 1. So on both of these, there's 2 of them. So keep that in mind. We're going to touch on both. So when x equals negative 1 and when x equals 1, we're going to touch at both of those spots. So x equals negative 1 and 1. So 3, we're going to find the, I should write it here, touch at both. So keep in mind that multiplicity, what's going to go on with the graph. So y-intercept now. So f of 0. Well, 0 to the 4th is still 0. 0 squared is still 0, so neither of those will be there. It ends up being y equals 1 for your y-intercept. 4, we're looking at symmetry. So if we put a negative x in here. Negative x to the fourth will leave us with a positive x to the fourth, so we're not changing. If we put a negative x into x squared, we're not going to change sign again. And the 1 is a constant, won't change sign either. So this one will have y symmetry. So it'll be symmetric about the y-axis. We'll be able to fold it over the y-axis and it would match. Lastly, turning points. Biggest number, biggest exponent is 4, so that's our degree. So we would do 4 minus 1 and get 3 turning points. Okay. So biggest exponent, you're going to subtract 1, and that's going to be how many turning points it'll have. So if we go to graph this now, start by, we're going to plot our x and y intercepts. So at -1 and at 1. We also know our y is going to be here at 1. So we're going to have those 3 points there. Now we know our ends are both going to be up. So it's going to do something like this. Where it's going to look like a W. It's going to be coming down, touch, go up, touch, come down, go back up. And this is what our graph would look like. It'd be something like this. And that's it. That's how far we go. Now, I know we only did one of these. We're putting this all together. So if you need to go back and watch this part, and if you have any questions, please let me know. But otherwise, we kind of went through and found each thing individually as we went through the lesson, and then we put it all together at the end here. So let me know if you have any questions. Otherwise, until next time, we'll talk to you later.